must time out or something, doesn't it?
Yeah, it only filmed for like 30 minutes.
Okay. So, one way you design, when you know every piece of material you have, you know the exact operating conditions that you're going to use. And what we do is we use a free body diagram, an FBD, to analyze it. Okay? So, you're going to be dealing with a lot of FBDs here, and that stands for free body diagram. Free body diagram. So if we know exactly what something's doing, like let's say we've got this over in the automotive shop, which is a stand, it's got a beam across the top, and we're going to use it to pull engines. So we're just going to put it on casters, slide it over a car, hook an engine, hoist it up, move it away. We know exactly all the materials and what we're going to carry with it. And we're going to put a thing on there, hey, you can't get this big as an engine on it. Now, if that's the case, what I do is I look at this item right here. Here's my draw. What I'm basically going to do is draw a free body diagram where we draw the beam. And it's usually a horizontal line. Okay. And then we use symbols to represent the forces that are going down. Okay. So in this case, what I would use is an arrow or a vector. Remember, vector is a line that shows direction and magnitude. So I put it here and I would call it a force, so like F, and then I use a subscript on the bottom. So we label all of our forces with subscripts. So in this case, the force of the engine. Okay, and we know that force, it's 1,000 pounds, right? Now what we then have to look at is we try to lay this member out and identify all the forces that are being applied onto it. And then we have what we call a reaction force, and these are labeled R's. Because for the ultimate thing here is that we want this beam to stay still, right? It doesn't move. We want the engine to come up. We want these supports right here to be able to support it. But this thing's got to stay static or not move. Okay. So, in essence, we know that these reactionary forces, and you might call them here R1 and R2. So the sum of our forces must be equal to the sum of our reactions. Does that make sense? Because we need it to be a static environment. So in essence, this is the best of all design worlds, where you know exactly what you got, you know all your materials, and you know how it's going to be used. There's no guessing room here. We can mathematically quantify this with a free body diagram such that this thing will work exactly right. Now there's another way that we do this, and that is where we don't know how something's being used. So I kind of put it in my notes here. Exact conditions are not known and they are guessed at through experience and regulating agency. I've always kind of chuckled at that and still am. Guessed at. Well, does that sound like a good way to go about doing a structure? Is let's guess. In essence, it's exactly what we do. No, it is. We have built enough buildings that regulating agencies have put out and said 99% of all structures will never exceed this weight. And we've measured 50 of them, and statistically that's the case it's going to be. Remember when we were doing architectural and we did the floors and we figured 40 pounds of load for every square foot of floor? That's in essence exactly what we're talking about. Now we're doing a deck. Your deck, we don't know exactly how many people are going to be out there. We don't know exactly of everything they're putting on, but we do have some codes if we don't know that, such as a deck has to be done where the live load, remember live load is a moving load, is 60 pounds per square foot. We will know the weight of the dead load. The dead load is the weight of the structure itself. But we're going to design it so we can calculate all that weight. If you do not know it, you have to use 20 pounds per square foot of dead load for a deck. And this is right in the IRC. Now, once we get through designing it, we're actually going to come through and do this. Okay? And I've got some different sketches here, just so you kind of get familiar with a free body diagram. Okay, so if we don't know, what we always do is we add dead load and live load. Okay, that's the BL plus LL. If we have something that is a continuous load across the beam, such as a concrete floor, such as a tile floor, something of that nature, we label a continuous load as a single line with just a bunch of them coming down, showing that this weight is evenly distributed across the beam. When we have a point load, we use a single arrow like a fridge. Let's say we're going to put a fridge out on that deck somewhere. Or we could say that fridge is going to have a bunch of bottles of wine in it or something of that nature, which can get pretty heavy. We would then be able to measure that and say that's a point load on there. We're going to be doing quite a few free body diagrams as we go through this. Any questions so far? Okay. All right, last thing I want you to kind of look at for today. Well, it's not the exact last thing, but it's pretty close. Yeah, it actually is. Factor of safety. Kind of hard to read that where it's tilted. Okay. This is a pretty big topic, actually. FOS, or factor of safety. And I've got a formal definition to it. A measure of safety built into the design to account for. Remember, we're guessing at some of this stuff, right? So we don't really know exactly how this is going to be used, so we're guessing, like 60 pounds at live, 20 pounds at dead, whatever. Okay. So when we do that, we're putting a factor of safety on it. The reason we give a factor of safety, one, variations in the structural item. Is every piece of concrete the same? No. Some might have a little bit more aggregate in it, some might have something else, right? The batch comes out of the batch plant a little different. Is every piece of steel the same? No. Okay, when they batch up one, they might have more carbon in one, more zinc in a different one, whatever the case might be. There's variations in this material. Wood, how many knots do you got in that board? Those are all variations. Unknown operation. We're not exactly sure. And then the last one's a biggie. What kind of risk are we willing to accept? Okay, what kind of risk? Here's the calculation that you use for factor of safety. You take the structural member strength. So what will the beam carry? What is its capacity? You divide that by the weight you're going to put onto it. Let's say I do that calculation and I get an answer of 1.0. What does that tell you? So we've got the strength that we're going to put on it, divided into the strength that the member is able to hold.
It's the exact required strength.
Okay?
It's the same as the required strength.
That's exactly what it's going to tell you, right? A factor of 1. Let me put it in different terms though. It also means your chance of failure is 50-50. Okay? It is, because technically if you rolled a nail across the top, you are now less than 1 and it's going to fail. Okay. So think of this really statistically. A factor of 1 means it's going to hold it, but if one thing happens, it's going to fail, because now you're going to exceed the weight, right? Okay, factor of safety of 1, you will never do a structure at that. The lowest factor of safety I've ever heard of on a structure is 1.1. They use a 1.1 factor of safety on the space shuttle. What happened to one of our space shuttles?
I'll say that doesn't make me feel more sick.
That's the lowest I've ever heard. When I was mining, we did all of our slopes. I was an open pit miner. All of our slopes were generally designed at a factor of safety of 1.2 because we wanted them to fail. Right? We wanted to go in, we wanted to mine something. When we pulled out, we hoped the whole slope fell in so that we didn't have to reclaim it. It naturally reclaimed itself. Okay, so that was a 1.2 that we used on all of our pit walls. And now we knew at a 1.2 with ours that we would get small landslides all the time. And it's just cheaper for us to mitigate those small ones in the hopes that we get a big one when we're done and save us millions in refixing that pit. Most.
Did that vary like with the depth of your guys' pit?
Mm-hmm.
Okay.
Yeah, we'd have setbacks. It varied with the ore bodies and all of that. But as a general rule, we were somewhere between 1.15 and 1.25. The rock, it was all different. But 1.2 is a good number. For the residential market, folks, you guys are going to be somewhere commercial, residential, 1.3 to 1.5. Because now we're talking people. And we are not willing to risk anything with that.
You said that for residential and commercial?
Yeah, for things people are going to use. Okay? So, people use. When I say commercial or residential, your house, commercial would be a restaurant like we're going to do, or I don't know, a Home Depot or a Winco. Yeah, no, well, space shuttle, there's a known risk there. Okay. Now, keep in mind, when I say, we're just going up by tenths here, but those tenths are magnifiers, right? Okay, so we're taking them up quite a bit more. You're going to find out that actually, we not only maybe inflate the cost 50% to ensure that it doesn't fail, but we also have codes written in that we can only use 30% of the strength, or 66% of the strengths, or 2/3 of the strength of any number. Because we don't want things to fail. We're going to overbuild them so that we don't get people killed. Because generally when those things fail, it's pretty catastrophic, right? So pay attention to this factor of safety. When we come into our beam design, we're always going to be checking that number. We'll put up, maybe we'll do a 6x12 wide flange beam on it. We'll check the factor of safety. It's 1.2. That's not high enough for us. We need to go to a bigger beam. But it's a good check on how things work. All right, so there's some of the background. Free body diagrams used to really kind of show the configuration of the forces on a structural member. We get rid of all the eyewash. We're just using simple lines and arrows to denote all of the things we have to design against. You have your 6 or 7 forces there. You got tension and compression, which almost every item is under all the time. Then you have the others like shear, torque, moment that an engineer would look at also on these items. And then lastly, we're going to make sure that the thing protects everybody involved with the factor of safety. Any questions on this stuff? Okay, what I'd like you to do today, please draw the plan view in the cross section. Okay. They don't have to be real detailed, but you're going to be using them left and right. I would put the number of the column, see on there where the columns are labeled? Keep those numbers, or at least that diagram around, because we're always going to be looking at, hey, what's the distance between column 1 and 2, 2 and 4, whatever the case might be. If you want to draw those columns in now, I can tell you we're going to be using those. When you have that column, So what that's telling you, you see the 8" by 8" HSS? Okay, what you're seeing there is the rectangle shape, and then the corner is this piece.
Do you want us to draw that, the hidden line?
Yeah,
On
I think you
the-
should.
No, well, like on the section.
Well, on the section view, this would be the top view, and this would be OBJ if we can see it, but we're not gonna be able to see it, so that's gonna be the thickness. When you're drawing the side view, it'll look something like this. And there'll be a little hidden line that's a 1/4 inch in right here.
Okay.
That's what I wanted to cover this morning. When you get those items done, at least through, halfway through those questions, then you're on your own time for today. Any questions for me?
So that column's built out of tubing then? Square
Yes.
tubing?
Yep, we're gonna use some square tubing. By the way, there's a bunch of these, if you wanna look through them, in the S section of those drawings. Because we have a lot of these in this building. It's kinda nice, we can walk around and look at all this different stuff. Anything else? All right, well, thank you for your time this morning. Going into structural. Be a good idea to have a calculator around for this class, by the way. All right, ask me any questions if you have them.